All right, in this lesson, we're going to be doing an experiment with a mass oscillating on a spring. And so we're going to get some data, and we'll plot the data, and we'll answer some calculations about that data. So let's start by getting some measurements here. So the first measurement we have is that this is a 1,000 gram mass. So that's 1 kilogram. So mass is 1 kilogram. Another thing that we need to do is we need to displace this mass from equilibrium. So what I'm going to do is I'm going to mark off, hey, look at this. 30 centimeters is our equilibrium position. So if you read the top of this, this is 30 centimeters. I want to pull it down, a good old down to, let's say 20. So if I pull it down to 20, then it's displaced 10 centimeters. So I'm going to let it go. Let it go! So now if you notice, it oscillates between 20 and 40. Now it's slowly dissipating energy, but we're going to ignore that for now. Another thing we're going to determine is the period. So let's watch this video really closely. 1 100, 2 100, 3 100, 4 100, 5 100. Alright, so it oscillated 2 complete cycles in about 5 seconds. So 2 cycles in 5 seconds. We're going to use that information to determine everything we can about this mass on a spring. Let's go. Alright, so now analyzing this mass on a spring, let's first determine what the graph looks like, the displacement versus time graph. So if you think about it, the mass started off by being displaced some value. Here is our x, and on the x-axis, on the horizontal axis, we have time. So basically what happened is that the mass started up here at 10 centimeters or 0.1 meters above its equilibrium position. So it was 0.1 meters. Then it went down to the 0 meter mark. Now in reality it went from 40 to 30 to 20, but we're going to call that 30 middle point 0, because we can pick any part as 0. So really this is 40, 30, and 20, or we could do 0.1, 0, and negative 0.1 meters. So now it started at 0.1 meters, then it went down to 0, aka 30, then it went down to 20, aka negative 0.1, or 0.1 below where it started, then it went back up to 0, then it went up to 0.1 again. That's one cycle. It did that again. It went down, down, up, up for 2 complete cycles. Those 2 cycles took a complete amount of time of 5 seconds. So it went down and up, down and up. 2 cycles, 5 seconds, bada bing, bada boom. Our period is, well, what is our period? To figure out period, we take the seconds that it moved divided by the cycles. In this case, our period is 5 seconds divided by 2 cycles, or 2.5 seconds per cycle. So each cycle took 2.5 seconds, about, give or take. Now, let's figure out our frequency. Frequency is cycles per second, or hertz. So frequency is cycles. In this case, it went through 2 complete cycles in 5 seconds. So that's 0.4 cycles per second, or 0.4 hertz. Man, just doing all this math makes my brain hurts. Oh my goodness. Okay, so now we have period and frequency down. Let's go through some more. I'm going to erase the graph here. And let's go with another calculation. Let's figure out the angular frequency. Angular frequency. Angular frequency is radians per second. Now the equation for it is 2 pi times the frequency. Well, our frequency is 2 over 5, so I can replace that with the f is 2 over 5. I'm going to use a darker marker that rhymes. Darker marker, 2 over 5. And we can just basically say 2 pi times 2 over 5, or 4 over 5 pi. Now you can calculate that if you want, And I'll just do a quick calculation with it now. 4 divided by 5 times pi, bada bing, bada boom, is approximately 2.5. Hey, that's kind of nice. Is that 2.5 for the frequency? No, 2.5 for the period, 2.5 for the radians per second. That's pretty cool. It's actually 2.51. That's pretty rad. Now, angular frequency is 2.5 radians per second. Our amplitude we already determined is 0.1 meters. So we're going to box around all these values. Now, let's go one step further. What's the maximum velocity that this thing travels? Well, it started at 0, then it went to some maximum velocity, then it went to 0 again, then it went to some maximum velocity the other direction. So the maximum velocity can be determined by, well, I erased that equation. But here's my Vmax equation. It's my amplitude times my angular frequency. And I have both those. It's 0.1 times 2.51. So 0.1 times 2.51, I can do that in my head. Carry the 1 divided by 11, square root of 13, is 0.251 meters per second. 0.251 meters per second. So that's the fastest that this object traveled was 0.25 meters per second. That's not too bad. That's pretty slow, actually. Then, going one step further, what about the kinetic energy? What's the kinetic energy, maximum kinetic energy that this object goes through? Well, the maximum kinetic energy, I can calculate that. EK is 1/2 mv squared. Now, 1/2 is just, hey, disappear, woo, I'm off the camera, I'm on the camera, okay, whatever. So, EK is equal to 1/2 times the mass, which is 1 kilogram. Don't kilogram, it's nice. 1 kilogram times our velocity of 0.251 squared. So, figuring all that out, we have 0.5 times 1 times 0.251 squared. And we get a value of 0.03. 0.03. That's joules. James Joule, good name. 0.03 joules. So that's our maximum kinetic energy is 0.03 joules. That's not that much energy. Doesn't take much energy to get this thing oscillating. What about our maximum elastic energy? Well, to figure out our maximum elastic energy, we need to figure out our elastic energy equation. Now, if you look over here, the equation for elastic energy is 1/2 kx squared. So I'm going to erase some information, because we're going to need all of this. And our maximum elastic energy is 1/2 kx squared. ES is 1/2 k, which is the elastic constant, how stretchy the spring is, times x squared. Now, this x right here, to find the maximum elastic energy, is just the maximum that x can be. And the maximum that x can be is 0.1. Just looking at the graph again. Look back at the graph and you found that the maximum x value was 0.1. So putting 0.1 into this equation for x, if I square 0.1, I get 0.01. Hey, that's kind of cool. So 0.01. Now I have to figure out my k value. How do I figure out k? Well, the only other equation that has k in it is this equation right here. The period of a spring. The period of a spring can be determined by the equation of 2 pi times the square root of the mass divided by the elastic constant. So as the mass goes up, it takes a longer time for it to oscillate. As the elastic constant k goes up, it's quicker because the spring is stronger. So I'm going to solve for k using the period of a spring. So period of a spring is equal to 2 pi times the square root of m over k. K, all right? So period of the spring, we already had that value. That was 2.5 seconds. We've measured that before. So this is 2.5. All right, we want to solve for k. Now the mass, if you remember, is 1. It's 1 kilogram. 1 kilogram. I'll put 1.0. Now I want to solve for k. A little bit of algebra here. To get k, Is that K if it's U? No, it doesn't matter. All right, so bad puns. All right, so 2.5 divided by 2. That's the first thing I can do is 2.5 divided by 2. That's 1.25 equals pi times the square root of 1 divided by k. Divide both sides by pi to get rid of pi. I don't know why you'd want to get rid of pi. Pi is tasty, but we'll do that. 0.398. 0.398. Get rid of the pi equals the square root of 1 over k. I have to square both sides, so I'll square this side, that gets rid of the square root. So if I square that, I get 0.158 equals 1 over k. Multiply both sides by k, that gets rid of the k on that side. Divide both sides by the 0.158, that gets k by itself. So 1 divided by 0.158, a lot of math here, equals 6.33. So K is 6.33 newtons per meter. That's not our answer, but that is a question we could ask. Like, how strong is this spring? Remember, the bigger that K is, the stronger the spring. 6.3 is not a very big number, so this spring is very, very stretchy. Now, going back to our equation here, plugging in 6.33 in for K, let's solve that out. What's the maximum elastic energy that this spring has? 1/2 times 6.33 times 0.01 is 0.03. It'll be joules. OMG. Why did I do all that math? Think about this. That's a lot of math. Let's think about energy again. This spring, this mass right here, started with potential energy. Quiet you. Started with potential energy. And then it went to kinetic energy because it was moving. Then it went to elastic energy because the spring was stretched. Then it went back to kinetic, then potential, kinetic, elastic, kinetic, potential, kinetic, elastic, kinetic, potential. Be a song. But no matter what energy I had, it was always the same value. It was always the same amount because of that first rule of energy. Energy cannot be created or destroyed. It just simply changes from one form to the next. So we start with 0.03 joules of potential energy. Then it goes to 0.03 joules of kinetic, which we just solved. Then it goes to 0.03 joules of elastic. And then back to 0.03 joules of kinetic. Then it just keeps going back and forth. Always 0.03, roughly. So, what did we just solve here? What did we figure out with this idea? Well, we found lots of information about this mass on the spring. We found out that energy is always conserved. So it doesn't matter how you calculate the energy. Once you find one energy, you found them all. We found out the relationship between period and frequency. We figured out, okay, how do we get period? It's just the total number of seconds divided by cycles. How do we get frequency? It's the opposite, cycles per second. We found out that you can find the angular frequency and use that to find velocity, use that to find kinetic energy. We found out that there's an equation for relationship between mass and elastic constant and period. Similarly, there's a relationship between period, length, and gravity with a pendulum. It's very similar. In fact, that's a later question I'll ask you, is how does the length of a pendulum affect the period of the pendulum? And it's kind of similar to the mass. And then finally, we applied all this together. So your assignment is to go to part 3 of the lab, and there's a simulation. And in the simulation, it's going to have you do some similar stuff. Similar stuff with the simulation, and answer some questions about this mass on a spring. So I'll show you the next part of the assignment and what to do for it. So I'll present here. Present, not future, not past, present. Okay. All right, so 5, 4, 3, 2, 1. Jordan for the win. All right, you guys can see my screen. Awesome. So here is It's Learning. You go to simple harmonic motion sound waves, bada bing, bada boom. And last week we did part 1 and part 2. This week we're going to continue with part 3 and then part 4. All right, so you guys will have a different screen than I will. It'll just pop right away. Let's talk about part 3. What's it look like? Espanol or Inglés? I don't know. So as this thing's loading, let's see what part 3 looks like. So we did part 1. Then as far as part 2 goes, we did everything except for part 5, except for question 5. Now remember, if you can calculate the length of the pendulum and show the work, I'll give you extra credit for that question. So keep that in mind. I'll go over the answer in class later this week when we actually get back in school. I have this video here to help you on part 3, but you can also just watch this video as well, and I think that'll be even more helpful. Now, for this part 3, it's a little bit longer. It's the longest part out of the 5. What you want to basically do is answer all of these questions on question 8. You have to collect some data, though. And the way you collect the data is you go to this simulation. And that tells you exactly what to do. We're going to turn damping off, which is turning off the dissipated energy. We're going to place a 100-gram mass on the spring. We're going to go through 5 complete cycles. We're going to time some stuff. So I'll show you kind of what we're doing here for part 3. And yeah, I'll kind of walk you through it. So what we want to do is go to lab. We're going to click on lab, and then we're going to place the 100-gram mass on there. Obviously, you can see there's some energy bar graphs here. I'm going to restart it, though. I'm going to turn off damping. So it's basically turn off the dissipated energy. Yep, turn it off. And then I'm going to place the mass on there. And you can see how it oscillates. Now, there's no dissipated energy there. We took it off. And then you can see the kinetic energy, potential energy is changing. So I'm going to click on a couple things to keep track of it. There's a ruler here you can use to make some measurements, just like we did in class. And there is a timer here you can use to get some accurate time measurements, rather than just me counting like I did in class. You can also slow it down, so I can time it really accurately. So I would time it at the very start, and then go through a couple cycles, and then stop it when it gets back to where it started. Kapow. All right, so you can play around with that. I can measure the lines here, and I can get a movable line, and I can actually like place that line wherever I wanted to. I can trace my period, so it actually will make it kind of like a graph, but it's kind of a weird graph, so I don't like that feature. You can change around with some of the variables. So if you want to increase or decrease the spring constant, you can change the mass if you wanted to. But keeping it simple, basically what we want to do is we want to go back and answer all these questions. So you can see there's some data we want to collect. We want to go 5 cycles, complete time it. You want to calculate all these things: the angular frequency, the what's the mass in kilograms, what's the period, what's the frequency, angular frequency, amplitude, elastic constant. We want to calculate all that stuff. So then you just show your work in part 3, bada bing, bada boom, put it right there, and part 3 is complete. So hopefully that all makes sense. I will help you out if you get stuck.